This video is about second derivative and its graphs. First of all, let's look at the following concepts. Fill in the blanks. Number 1, when the first derivative f prime of a equal to 0, the point a, f of a could be minimum, maximum, or stationary inflection point. When first derivative greater than 0, the function is increasing. When first derivative less than 0, then the function is decreasing. When second derivative f of a equal to 0, the point a f of a is a inflection point. If second derivative of x has a sign change, at x equals a. When f double prime of a equal to 0, the point a f of a is not an inflection point. If second derivative of x has no sign change, at x equals a. When second derivative of f of x greater than 0, then the f of x is concave up. The graph like this. When second derivative of f of x less than 0, then the function f of x is concave down. The graph like this. Let's go over this diagram. When first derivative less than 0, this is a decreasing. When the first derivative greater than 0, this is an increasing function. When the first derivative equal to 0, it could be maximum, minimum, or stationary inflection like this point. When second derivative of f of x is negative, which means it's concave down. Then the second derivative of fx greater than 0 is concave up. When second derivative of f of x equal to 0, it's a inflection, either non-stationary inflection or stationary inflection. You have to make sure the second derivative of fx, the sign diagram at x equals a, either from positive to negative, or you have a negative to positive. In other words, inflection point is where concavity changes. So from this diagram, we could say at a stationary inflection, the first derivative equal to 0 and also the second derivative equal to 0. Now let's go to guided practice 6. Find and clarify all points of inflection of f of x equals negative 3x to the fourth power minus 8x to the third power plus 2. When you talk about inflection, means the second derivative equal to 0, which means the second derivative of f of x equal to 0. First of all, we will get the first derivative equals negative 12x to the third power minus 24x squared. Then the second derivative of x equals negative 36x squared minus 48x. Then we need to set up this equal to 0. Common factor. It will be negative 12x, 3x minus 4 equal to 0. Therefore, x1 equal to 0, x2 equals to 4 over 3. Then check the sign. Let's draw the sign diagram. We have 0 and 4 over 3. Let's check 1. So when we plug into this negative 12x, 3x minus 4, you will get positive here. Because the second derivative of f of 1 equals 12, that's greater than 0. For this 0, we know this is a single factor, therefore this is a change sign negative. 4 over 3, same thing, we need to change sign. This is a negative. Since at x equals to 0 and 4 over 3, second derivative of x has a sign change. Now we can figure out f of 0, plug into the original function. You can get f of 0 equals 2. And f of 4 over 3 equals 3 times 4 over 3 to the fourth power minus 8, 4 over 3, third power plus 2. After we put into calculator, you will get a negative 202 over 27, which means we have a coordinate 0, 2 and 4 over 3, negative 202 over 27. These 2 points are inflection. Now let's go over the procedure. First of all, you will get the first derivative and a second derivative. Second step, you will set the second derivative equal to 0. Solve for x. Then make sure you have to do the sign diagram to make sure the second derivative has a sign change at the roots. Then you plug in to the original function to get the coordinate. The last step, you will write down the coordinates for those inflection point. Guided practice 7, consider this. Find and classify all stationary points and points of inflection. Stationary points means maximum or minimum or stationary inflection point. We will figure out the first derivative of the given function. You will do the derivative for this and this, this and this. You will get 6x squared minus 6x minus 36. Then we will figure out the second derivative. You will get the 12x minus 6. when you're looking for the stationary points, you will set up the first derivative equal to 0, which means 6x squared minus 6x minus 36 equal to 0. We have common factor 6. So we have x squared minus x minus 6 equal to 0. Factor x minus 3, x plus 2 equal to 0. Therefore, you get the x1 equal to 3, x2 equals negative 2. Then we plug into the original function, f of 3 and f of negative 2. After we plug into the function, you will get 3, negative 74, and negative 2, 57. Then you need to decide these 2 points, which one is a maximum point, which one is a minimum point. There are 2 ways to decide maximum point or minimum point. First of all, we can use first derivative f prime of x. We draw number line. We have negative 2, we have 3. We plug in 0. You will get negative times positive equals negative. So here's a negative. Since x minus 3 and x plus 2 both are single factor, that's why we need to change the sign positive or positive. Then the graph will be going up, down, then going up. So this negative 2, 57, that's the maximum point. And 3, negative 74, is a minimum point. Another way to decide the maximum or minimum point, we can use a second derivative. We plug 3 into second derivative, you will get 12 times 3 minus 6. This is a greater than 0, which means it's concave up. Therefore, 3, negative 74 is a minimum value. Then we plug in negative 2. You will get the 12 times negative 2 minus 6. It's less than 0, which means concave down. In other words, for negative 2, 57, that's a maximum point. Now let's go to find the points of inflection, which means you have to set up the second derivative equal to 0. 12x minus 6 equal to 0. X equals 1 over 2. Let's check the sign diagram. We have 1 over 2. So greater than 1 over 2 is positive, less than 1 over 2 is a negative. Therefore, we plug into the original function to find the coordinate. Therefore, 1/2 negative 23 over 2 is a point of inflection. Now let's go to B. Find the interval where the function is increasing or decreasing. We need to draw the sign diagram for the first derivative. Basically, we already did that when we're working on A. So we have negative 2, here's a 3. Then this is a negative or positive, positive. In other words, this is increasing, decreasing, increasing. So we can write down the solution. from negative infinity to negative 2. And from 3 to positive infinity. This is an increasing interval. And from negative 2 to 3, that's a decreasing interval. Now let's go to number 3. Find the intervals where the function is a concave up or concave down. You just need to check the sign diagram for second derivative. We have 1/2. Then here's a positive. This is a negative, which means concave up, concave down. So we can write down from negative infinity to 1/2. This is a concave down. From 1/2 to positive infinity is concave up. Let's go to D. Sketch the graph of y equals f of x, showing all important features. We already know minimum, maximum, and inflection point. We use these 3 points to sketch the graph. We'll plot these 3 points, and then you can sketch the graph, increasing from infinity to this negative 2. Yeah, this is the graph we sketched for this function. Let's go to guided practice 8. Consider f of x equals x plus natural log of x. For what value of x is f of x defined? We know for logarithm function, the argument must be greater than 0. So we can write down x greater than 0. B. Find the sign of the first derivative and the second derivative and comments on the geometrical significance of each. So first of all, we will working on the first derivative. That is 1 plus 1 over x. Multiply by x. So you get the x plus 1 over x. Then for the second derivative, you will get x plus 1 over x. Then you have to use the quotient rule, so x squared as denominator. You will get x plus 1 derivative times x minus the x we do derivative times x plus 1. So you will have x minus 1 over x squared, which means negative 1 over x squared. So we got to do the first derivative, the sign diagram. You have to get the all roots and the vertical asymptote line. So for roots, you only have x equals negative 1. Make a top equal 0. That's x equal negative 1. Make a denominator equal to 0. Then that's x equal to 0. This is a vertical asymptote line. So we draw the sign diagram. Remember the domain for the function is x greater than 0. Therefore, for this roots, x equals negative 1, we don't count that. We only draw x equal to 0. This is a open parenthesis. That's a 0. We plug in 1 to the first derivative function here. Then that's a positive. So the graph is going up. 0 is a vertical asymptote line. Now let's draw the sun diagram for second derivative. The roots, we make a top equal to 0. -1 never be 0, so roots is not available. Vertical asymptote line, still x equal to 0. So here's 0. We choose 1. You could say it's a negative. That means the graph is like this. It's concave down. In other words, for the graph, this part, it will be like this, not concave up. So normally we use the second derivative to decide the pattern of the curve. Now we're working on the geometrical significance of each. From 0 to infinity, it's all increasing. And for this interval, this is a concave down. Let's go to D. Sketch the graph y equals f of x. We already know this is a concave down and increasing. That's why the graph will be like this. Now let's go to E. Now let's go to D. Find the equation of normal at the point where x equals 1. First of all, we will plug into the original function to figure out the coordinate x1, y1. 1 plus natural log of 1, that equals to 1. So we have 1, 1. That's our x1, y1. Then we plug into the first derivative. That will be the slope of a tangent line. You will get the 1 plus 1 over 1 equals 2. So we get the slope of a normal line. Do the opposite reciprocal, that's -1 over 2. For the equation, we have y minus 1 equals -1/2 times x minus 1. That's it.